time to start. So the third speaker of this afternoon session is Enis from Katholieke Universiteit Leuven. And we speak about p-adic integration theories on curves.
Okay, thank you for the introduction. I think Leuven is part, Leuven part is fine, but not Leiden, Leuven. Leuven. Yeah, I'm not Catholic. Anyway, well, thank you for the introduction. Also, I want to thank organizers for creating such a beautiful atmosphere and letting me a part of it. Well, thank you. So most of this is a joint work with Eric Katz from the Ohio State University. Here is the setting, fix an prime number p, and for explicit methods, this will be an odd prime number. And by x, we will denote a nice algebraic curve divided over qp. Most importantly, it's smooth. And then we take a differential bond form on our curve x. And we fix 2 points, x and y, in our curve. And then when it makes sense, we are fixing a path inside our curve, because sometimes x is going to be an analytic curve. The most important definition is p-adic integration theory. This is a method on x for defining integrals of this form, which take value in qp bar with reasonable properties. For example, we want additivity in endpoints, we want additivity in integrands, we want fundamental theorem of calculus, we want functoriality, etc. So maybe this sounds a very trivial thing. Well, this is not the case. This is highly trivial. The main reason is that the naive analytic continuation is impossible. This is because of weird topology that Farbod is explaining since Monday. However, thanks to some legends in the area, we have some reasonable integration theories. And the first one is a Coleman. It's denoted by this symbol. It's an integration theory along points. And it assumes that the curve in the question is good reduction. And the language is rigid analytic. If you don't know what this means, you can just think of as a Berkovich space. That's fine. But one of the posters is about rigid analytic spaces, so you can just go there and check for information. And the second legend is Vygotsky, and this is the corresponding notation. This is also along points. No assumption on the reduction type, and the language is algebraic. And the final one, this is the Berkovich integration. This is the symbol. This one is along paths, no assumption on reduction type, and the language is Berkovich analytic. In the special case where we have good reduction, we can apply all of this, and it turns out that all of them are the same, so things become more interesting in general case. Because in general, Vygotsky integration and Berkovich integration are different. And my first goal today is to present a formula passing between them using tropical integration. So Coleman integration and Vygotsky integration, they have numerous applications in arithmetic geometry. I just want to name 2 of them. First of all, we find them to compute rational points on curves of genus at least 2. There is one method called Chabot's method, non-abelian Chabot, quadratic Chabot, which are quite famous these days. And these methods are based on p-adic integration, for example. And it's also possible to define and even compute p-adic analogs of classical height functions, height machines, and also regulators. So it's possible to, for example, to formulate p-adic version of Birch-Simon Dyer conjecture. Instead of classical regulator, you put p-adic regulator. And it turns out that these applications rely heavily on explicit computations for a given curve, differential form, endpoints. You want to compute these integrals numerically. You want to approximate these integrals. And the good thing is that in the good reduction case, things are quite suitable for machine computation. There is an important map called Lifthoff-Frobenius. As long as you can compute this, as long as you can compute its action on differential forms, you essentially know how to compute these integrals. And that's why we have nice algorithms in the area, and these are implemented in nice programs. However, Vologoski's construction is highly abstract. There is no direct way to compute this. But in this talk, I'm going to give you an algorithm to compute these integrals on hyperelliptic curves using some indirect approaches. And finally, the third goal, I want to discuss an extension of this algorithm to deal with more general planar curves, and hopefully some of these curves will be interesting for tropical community. So, our fixed curve, it admits a semi-stable model, by which I mean the following. So remember the picture that Farbod drew. So here we had Z instead of ZP. Now I am adding ZP. Right now we have 2 points. So there should be 2 fibers. The first one is generic fiber. It's isomorphic to curve we started with. So this part is not interesting at all. And the second part can be seen as your curve modulo P, reduction. And semi-stable means that we have the nicest singularities. Okay, so all singularities are nodal. And the good thing is that such a model always exists. Sometimes we just need to enlarge the field a little bit and apply some notions from algebraic geometry. So what is the dual graph? Here we have special fiber. We just dualize this in the sense that for every component, there should be a vertex. And by looking at how they intersect, we just add edges. Yeah? So Xn stands for the Berkovich analytification of our algebraic curve. And today, again, Farbod mentioned 2 important things one can attach to this data, namely the skeleton of our Berkovich space and the retraction map from Berkovich space to skeleton. I'm going to use this symbol tau for that. Just a few words about these things. Gamma is homeomorphic to the dual graph of the special fiber. In other words, inside our Berkovich space, we will see a copy of this graph. And tau is essentially the dual of the reduction map. Let me give you an example. So here we have a bed reduction hyperelliptic curve defined over Q17. So as you see, when we look at the same curve modulo 17, the first and last roots, they just collapse, right? So this is a picture we will get. So the dualizing this, we get just one circle. And this picture, this beautiful picture due to Joe Robinoff, it represents the corresponding Berkovich space. And as you see, there is a cycle inside our space. And there is a formal way of defining tau. Again, Farbod did. But let me give you an elementary school definition, at least on this picture. Let's take a point, maybe here, somewhere on the Berkovich space. Its image on the skeleton is just closest point. That's it. Basically, we just want to keep track of some paths on our Berkovich space on the skeleton. So one nice thing about Berkovich integration is that it's local in the following sense. Consider the following situation. So right now, I want to see my Berkovich space kind of p-adic manifold. Of course, this picture doesn't make any sense, but you see what I mean. And imagine that the path along which we want to compute the integral lies in a subdomain U. So in this case, instead of computing this integral over the ambient space, we can just consider U. We can just work locally. This is not surprising in the sense that I'm sure that you expect this, but the interesting thing is that for Vologoski integration, this is not true. And it gives us a hope to compute these things easily. So here we fixed gamma. This is a finite and connected graph. In principle, this is going to be the dual graph of a special fiber. And E of gamma denotes the set of oriented edges. We have a finite graph. For every edge, we also have its inverse. This is the same edge with reverse orientation. So a tropical one form on gamma, it's a function from the set of oriented edges to Q, such that eta of minus E is equal to minus eta of E. So once again, we have an edge E. Then minus E is the same edge with reverse orientation. And also, we need some kind of balancing condition. For each vertex V, we look at the edges that are directed away from B. And for each one of them, we compute eta, then we consider the sum. This sum should be 0. Okay? And the space of such functions is denoted by this symbol, tropical one-forms on gamma. These are tropical forms. So let's fix such a form, and let's consider a path inside our graph specified as a sequence of edges, E1, E2, all the way up to EL. Then the tropical integral of eta along this path, denoted by this symbol, is nothing but the sum of the edges. Yeah? 3 years ago, when I was in Berlin visiting some people, including Marta, we were discussing this in her office, and I couldn't remember the definition of tropical integration. Of course, that was the maybe most important, interesting part for her. So now I can answer your question. It's been 3 years, sorry, but this is how we define them. So how do we compare them? Let's fix a semi-stable model. It's not unique, of course. And let gamma and tau be the corresponding skeleton and retraction map. We need one more result before the comparison theorem. So first, we proved that there should be a basis containing Ci's of the cycle space in our graph, and a basis eta j's of the tropical one-form space. In particular, they have the same dimension, such that the tropical integral of eta j along Ci is delta ij, the Kronecker delta. It's a kind of computing a dual base. Okay? And finally, the comparison theorem. We fix a meromorphic one-form on our curve, 2 endpoints, x and y. And since we are in a nice setting, our Berkovich space is path connected, and we pick a path in our space from x to y. So the Vologodsky integral on the left-hand side is equal to Berkovich integral on the right-hand side, minus what we call correction term. And this correction term, it consists of some tropical integrals plus some Berkovich integrals along closed paths. So kind of Berkovich integrals, Berkovich periods, right? These are some closed paths. So let me just say that this is a reformulation of some results due to Katz, Robinoff, and Zurich-Brown for holomorphic forms, and Besser and Zerbes for meromorphic forms. So the original theorems were not suitable for explicit computations, so we just wanted to reformulate this in this way. Yeah? So basically, what is important about this? For applications, we want to compute Vologodsky integral, and in practice, it's quite easy to compute tropical integrals. And this theorem tells you that you can just compute a bunch of Berkovich integrals, but this is kind of doable because this integration is local. Yeah, this is the advantage. Okay, what is the algorithm? Let's fix an hyperelliptic curve x over qp. Thanks to comparison theorem, it's all about computing Berkovich integrals on our Berkovich space. How do we do this? So we used a semi-stable model. There is another notion in the literature called semi-stable covering. These are essentially the same. The advantage of coverings is that it's just more explicit. Instead of some bunch of abstract objects, we just work with some subsets. We first construct a subset of our Berkovich space such that every element in the covering, it can be embedded into another curve denoted by xi, such that this is either a rational curve, isomorphic to P1, or it's an hyperelliptic curve of good reduction. Okay? So now, whenever we have a path over which we want to compute Berkovich integral, we just write this as a concatenation of smaller paths, each of which lies in just one component. So we just use the localness, and we want to do everything on UIs instead of these big complete curves. Then using functoriality, we embed everything into xi's and do computations there. So it's all about computing these integrals on xi. Well, in the first case, we can just parameterize xi. We can express everything in terms of one single parameter. Then integration is super easy. It's just term by term. Otherwise, we just make use of known Kalman integration algorithms, right? Because otherwise, we have good reduction curves, and we already know how to deal with this. So let me give you a numerical example. Again, we consider the same curve. And omega is dx over 2y, the invariant differential. And we have two endpoints, r and s. So far, I didn't say anything about the construction, but let me just say that if the integrand is holomorphic, then it's all about formal logarithm computation. But this is super explicit for elliptic curves, and they are already implemented in Sage. So if you just write a few codes, you can easily compute this example, integral, and this is the number you will see. It's just maybe 7 or 8 lines. And the goal in this example is to compute the same thing using the comparison formula. So how do we get the covering of our space? Well, first we, as usual, I mean, there is a nice map for our curve, right? This is just pi. This is the double covering map. And we first construct a nice model for P1, U1 and U2. As you see, they intersect in an annulus. So this is the corresponding tropical picture. We have two components. They intersecting in just one annulus. Then we just move everything back using pi inverse. Since this is a double cover, the inverse image can be 1 or 2. In this example, again, we get two components. But this annulus splits into two annuli. So this is the picture. And S and R, respectively, belong to V1 and V2. Let's choose the orientation like this. As you see, we have just one cycle inside gamma, E1 plus E2. Hence, there is only one correction factor. This is the comparison formula, right? There is only one Berkovich period where the corresponding tropical integration is just going to be 1 over 2. And gamma is any path in the Berkovich space from S to R. We want to construct this path, and of course we want to do, this thing nicely. And here's the construction. In order to pass from one component to the other, we pick a point first, and then we define gamma as the concatenation of two paths, gamma 1 and gamma 2, where the first one is from S to P in the first component, and the second one is from P to R in the second component. And the whole thing is nice path whose image on the retraction map is just E1. So maybe it's not easy to follow this recipe. Let me show you this beautiful picture. We want to go from S to R, but first we go from S to P, then P to R. Yeah? So gamma is union of these two. So this Berkovich integral is the sum of these smaller Berkovich integrals. And by construction, every small path, it lies in a single component. Nice thing is that Berkovich integral is local, so we can just work locally. The advantage is that both of these components, they can be embedded into P1. So we can parameterize everything, so take integral term by term and compute this nicely. So using this technique, this is the corresponding Berkovich integral. We play the same game for other integral. We combine everything, get this number. I don't know if you remember, but this is the same result as above. Yeah? So we computed the same integral using two distinct techniques. One of them is based on comparison theorem. The other is based on Sage math. And the conclusion is that Sage math is correct. Yeah. Okay, so the final part, we want to extend this to more general curves. Dealing with some curves like super elliptic curves, that's not a big deal, but we think that we can do much better using some ideas from tropical geometry. So here the setting is slightly different. Let's fix a finite extension K of QP. And we have the corresponding valuation and absolute value. And by P, we denote a nice polyhedron inside R2. I mean, we should put some conditions on P, but please ignore them for now. Since we are dealing with curves, this is just inside R2. And sigma is the recession cone of P, okay? The cone of unbounded edges. So we define a set denoted by this symbol. So here we consider all series in x and y with coefficients from k, where this sum is taken over all integral points inside the dual of the recession cone, such that the condition here, it holds, and we will see that it's a kind of convergence condition. Maybe this is weird at the first say, but let me give you why we care about this. First, every element in this ring, so we have the corresponding norm. For such an element, we just exponentiate the quantity here, and we get this soup. Yeah? And this soup makes sense because of the condition here. So this is nothing but the completion of the semi-group ring that we like a lot to construct affine toric varieties with respect to this norm. So this is a K-Bana algebra. Okay, why do we care about this? Because this is a K-affinoid algebra. So what is this? In the classical algebraic geometry, we use spectrum of rings to construct affine varieties. And in the classical rigid analytic geometry, we consider the maximum ideals of affinoid algebras. So these are kind of building blocks of our space. And this norm is nothing but the subnorm on rigid analytic spaces. So the bottom line is from tropical objects, we can get some rigid analytic objects. So for a given F1 inside this ring, which can be very complicated in general, but remember the example I showed you, we define approximation data. This is a tuple, including so many things, but more importantly, one more polynomial, such that their difference with respect to the new norm is kind of small. Okay? And we want to just think of F1 as being complicated and F2 as a simpler polynomial. It's all about getting approximation. And using this Fi, so first we consider the quotient ring, take the maximum, minus some beta ramification locus, which we don't care right now. Or in other words, so this is just a very affine variety corresponding to Fi intersected with the inverse image of our polyhedron under the tropicalization map. So thanks to this, we want to use the power of rigid spaces and tropical geometry at the same time. Sorry for going over time, but I'll be done in 2 minutes. So the first theorem we proved is that there should be a nice morphism from easier variety to harder variety, more complicated variety, where we can fix the x coordinates and the image of y minus y, so their norm, is bounded in terms of the approximation data. Okay, once again, it's all about getting nice approximation. So this is the diagram, which should be thought of as a parameterization of the main variety we want to deal with. And of course, this is more interesting if we have the case where T is an isomorphism. Yeah? Otherwise, we are going to miss some part of variety. And we prove in our paper that if F1 and F2, they induce right type of curves, okay, then this should be an isomorphism. So examples introduced by Tevelev. Today we have seen them in Kris lectures. So these are nice enough. And maybe one equivalent definition is that this variety is shown if for every W inside the tropical curve, the corresponding initial degeneration cuts out a smooth hypersurface. This is one of the equivalent definitions. What is the problem with this? The problem is that this is too restrictive. So quoting Farbod again, let's say if you want to walk along a beach, Copacabana beach if you like, and if you see a curve, it's not going to be shown. Yeah? I tried, I couldn't find any. So the expectation is that we can do much better and weak with weaker curves. And the current definition is that the variety is net. I'm going to explain what this means in a second. If for every W inside the tropical curve, if it's not vertex, again, we want the same thing. Okay, it should be smooth. So otherwise, it should be reduced. And for every irreducible component, the projection to x coordinate, it should be separable. We believe that these are highly important. And the second condition is that there should be a lift that satisfies a Tightman condition. So this is a completely different paper. Unfortunately, I don't want to explain more, but we can talk about this later. It's all about existence of certain matrices that provide integral basis for the function fields, both for the original curve and for the lift. The main idea was to give an algorithm to compute zeta functions. Okay? And I mean, if you use that data, you can just construct good compactification, as in the definition of Schönness. Yeah? So this is what, I mean, I think this can be weakened a little bit, but anyway. So net is a German word. It means kind of, it's okay, you know, yeah, not bad. Yeah. So, and this was independently suggested by Arne and Felix, sitting there and smiling, yeah. And also by ChatGPT. But of course, if you have other suggestions, that's also welcome. Yeah, thanks it. Obrigado.